So, we finished off last time with screening of this set on expressive behaviors, correct? And we, if you recall, and if you go through and take a look at your output, so we had in that data set that we were working with, we had 3 cases where we didn't have data on levels of expression, leaving us with a set of 189, is that right? Yes. Okay. So recall that we had gone through and screened this. I've posted a screening example of a Factorial ANOVA on the course website. Go through and take a look at it. That one's going to be a 2x4. So in a 2x4 factorial design, how many groups do we have? In a 2x4, how many groups? How many cells? What is it, Laura?
8.
8. We have 8 groups. That can make for a long screening. And so thinking about, as you're going through this, wanting to make sure that you're getting enough information, but if things are looking fairly unremarkable, you can start to condense things and say, yeah, all the histograms looked good, or sort of X, Y, and Z. So go through and wanting to go through, probably be helpful to go through, take a look at that screening. There's also an example, a screencast video I posted on YouTube. I'll give you guys the link so you can go through and take a look at that. So, but for this set, remember what we've done is we've got, we brought people in and we've randomized a group of participants to either watch a sadness film or a humor film. So either they're watching a funny film or a film that is intended to elicit feelings of sadness. And we're also, then the other condition here, we're randomizing people to either watch the film naturally or to inhibit all expression and emotion, right? So if we're watching them so as though I couldn't be able to tell you that you were feeling anything at all, right? And so we end up with 4 cells in this 2x2 design. We've got sad express, sad withhold, humor express, and humor withhold. We've gone through, we've screened, we've said everything looks pretty good with the exception of homogeneity of variance stuff. We didn't take a look at that in the screening. But our research question here, and we're using, so I'm working off of this 2x2 ANOVA handout. Here, the expressive behavior stuff. So our question here is what's the relative impact of expressive inhibition, or what's the relative impact of inhibition on behavioral expression in response to positive and negative stimuli, right? I'm an emotion researcher. I want to know, maybe are people sort of equally good at inhibiting expression or regulating expressive behavior in response to both positive and negative stimuli, okay? And so what I'm expecting, my hypothesis here, is that withholding is going to have a larger impact on the expression of amusement than on sadness, okay? So my working hypothesis in these analyses is that we're going to see inhibition impacts expression of amusement to a greater degree than sadness. Okay, that's my hypothesis. That's what I'm expecting to happen within the context of this design. Okay, what am I hypothesizing here? Is that a main effect or an interaction? Is it? This is an interaction. Why does this hypothesis involve an interaction? Yeah. On the amusement versus sadness, right? Like I'm saying, the impact of one condition my express versus my hold, that difference is going to depend on, or is going to be different whether or not we're talking about if I'm showing people an amusing film or I'm showing people a sadness film, right? And because we've got the impact of one factor on my outcome is going to change or be dependent on the level of my other factor, we're talking about an interaction effect here, okay? So this is really what I'm interested in at the end of the day. So we've gone through and we've screened these data. Remember, we've got film condition 0-1, instruction condition 0-1, and then we've got a behavioral code of expressive behavior based on raters going through and watching these people watch this film and then coding their behavior, where 1 is no expression at all, 5 is sort of lots and lots of expression, okay? So what we're gonna do, we've gone through and screened, and we're gonna now go through and actually run our analyses. So I'm going to go to Analyze. I'm going to go to General Linear Model, and I'm going to select Univariate. Okay. So now we've got a little bit different box going up here because we've got a couple of different factors. So our dependent variable, Amelia, what's my dependent variable here?
This would be should be the
expression rating, right? That's my outcome, all right? And John, what are my factors here?
The condition variable?
Yeah, which condition variables? Because I got 3 of them. Which one am I going to plug in there?
Just the condition one.
Okay, is that what? Haley, you're shaking your head. No. What'll happen if I run it? Just plug that condition variable in there.
It's like an error because it's essentially just a t-test and
Yeah.
two, like a one-way ANOVA.
Yeah, I mean, I just ran a one-way ANOVA because there's 4 groups. Remember, that condition variable is where we split people into our 4 cells so we could go through and we could screen, right? So Haley, what do I need to drop into that into my my IVs or my factor variables?
Your film condition and your
My film condition and my instruction condition, and we're going to drop these into fixed factors, okay? Now, there are different random factor designs that we could get into or not, but there are a number of additional things that you could go through. You could also turn this into an ANOVA-ish model. If you had some continuous covariate, we could drop down into there. Again, we're not going to worry about that right now because we don't have the time, but these are some additional options as your designs start to get more elaborate. So we've got our dependent variable, our 2 factor variables here. And so what I'm going to do is just go through and explore. We've got a full factorial model here. If you wanted to do some sort of different model or use a different type of sums of squares, this is where you would do it. Don't do that unless you have a good reason for doing it. Contrasts. Now you find that within a factorial design, SPSS won't give us planned contrasts the way that we've been working with planned contrasts. There are some other things it'll do, but those are often pretty limited and aren't super effective. So what we end up having to do is think about our strategy and do some of this stuff by hand or through other analyses. So we're going to ignore that for right now. Here we've got some different plots that you can go through and take a look at. Again, we won't worry about this too much because SPSS sucks at plotting things out. We're going to do this by hand based on what we get in terms of our output. We also have post hoc stuff. I'm going to give you guys a screencast video working through some post hoc analyses, and we'll talk about why, in general, within the context of a factorial design, this is not something that you should be opening up at all. Save, different things we can go through and save. We won't worry about that. And then options, this is where we're going to request some additional stuff. So we want to go through, we'll ask for marginal means for film, for instruction, and the interaction. This is going to help give us an idea for kind of what's going on in terms of different effects that we might go through and take a look at. Then we're going to go through, we're going to request descriptive statistics. We're going to request estimates of effect size. And then we're going to request homogeneity of variance tests here. Okay. Then we're going to hit continue. You guys hit paste. I'll go ahead and hit OK. But this is our, and so here's the output we're getting. All right. So someone tell me what we're looking at what we're looking at here. What do we got going on up here?
The mean ratings for expressing withholding within each condition, as well as the standard deviation and how many individuals there are in each.
Okay. Always go through and take a look at this, because sometimes you put the wrong variable in there. You want to make sure that your factors make sense, that you're interpreting them correctly, that you've got the right number of people in here. Again, and this descriptives table is going to be important, okay? Here we've got, for people in the sadness condition, we have mean expression level for sadness express, sadness withhold, and then what's this total, Evelina?
Is it the average for expressing withhold?
Maybe not the exact average. Why isn't it the exact average? Because the sample sizes are different. What's that? It's going to be a weighted average, or this is just the average score for everybody in the sadness, right? So, and then same thing for people who are watching the amusement film, the express, the withhold, and then the average of people in there. And so what are we, if we look at this total here and this total here, what do those means correspond to? What type of effect? What do you think, Andy?
Main effect?
It's a main effect. A main effect of what?
Film condition.
Yeah, this is a main effect of film condition. On average, do people who watch the sadness film express more than people who watch the amusement film collapsing across inhibition group? Okay. Haley, help me out here too. What about these? So what's this total express withhold? What are we looking at right here?
Would that be your interaction effect?
Not quite. So this is total. So for collapsing across film condition, this is the mean of what?
Of everyone in express.
And okay, and so what are we looking at there?
The effect of instruction.
Yeah, it's a main effect of instruction, right? So it's important, you want to be able to go through and take a look at your table and be able to see where are the means that correspond to my main effects, my interactions. My main effect, and Nick, where are my means that are going to go into any interaction effect that I'm looking at?
Well, your main effect will be your total means.
Okay, yeah. So I've got a main effect here, and I've got main effect here. Where's my inner? If I find an interaction in here, where am I gonna be looking at in terms of means for that?
That would be within your conditions.
Yeah, my individual cells, right? So here, my 2 by 2. Those are my interaction. Those are means that would go into interaction, right? But if I'm looking at a main effect of film, right? This is looking at overall ratings of people who watch the sadness film, overall ratings, expression ratings for people who watch the amusement film, irrespective of instruction condition. Here, we've got everybody who was told to express, irrespective of what film they watch, everybody who was told to withhold, irrespective of what film they watch. Here we've got our means for our main effect of instruction condition. And then what's this total? What's that down there? What's up?
Grand total.
Yeah, this is my grand mean, right? This is the grand mean. When you go back through those hand calculations that we did, anytime you say subtracting things from the grand mean, that's the grand mean right there. That's the mean expression rating of everybody in the study, okay? So this is going to be very, very important that you're able to take a look at this and be able to tell where these means are going from and where they want to, where they start to fall out, because this can start to get really tricky, okay? So, other thing, Kate, we're seeing here is our Levine's test. What are we concluding from our Levine's test?
Wasn't it like more significant if the closer you are to unequal variances?
Okay, so, yeah, restate that. So do we have a problem with homogeneity of variance here or not? What's that?
Yeah.
Yeah, we do, right? Again, remember that anytime I see a statistically significant effect, it probably means that something's not zero, right? And so we're talking about the differences in variances across my cells. I want that to be zero, right? But it's not. It's statistically significant, suggesting that, again, if we're thinking big picture about this, it's saying how many populations am I sampling from in this experiment? Within Kimberly? How many hypothetical populations am I sampling from? Getting closer? 4, right? So I've got a hypothetical population of people who inhibit their expression in response to a sadness film, and people who, a hypothetical population of people who naturally express. I've got a hypothetical population of people with hold to amusement, and a hypothetical population of people who just express. I've got 4 different populations, right? And the distribution of expression has a distribution within each one of those populations, right? And so what I'm wanting to know is, is expression, as rated through observer ratings, is the variability of those ratings equal across these populations? This is saying, based on the sampling data that we've got here, probably not, okay? So this starts to have impact in thinking about how we go through and start to approach breaking down any effects that we've got here, right? Laura, how are we doing in terms of a balanced design in this study?
Okay.
Yeah, we're not too bad. It's not perfect, but it's close. I'm going to call this functionally balanced, given the sample sizes or the cell sizes and stuff. I mean, we've got some discrepancy, but it's not too bad. But we do have a violation of homogeneity variance, and so that's going to start to inform how we move forward and start to tease some of these analyses apart. Okay? Questions on any of that? All right. So now we get into some of the meat and potatoes of this omnibus test here. Someone tell me, John, help me out here. What are we seeing in terms of my between subjects effects here?
It's looking like everything's significant except for the interaction.
Okay. So tell me, so everything is significant is kind of a
Yeah.
it's kind of a general term. Tell me exactly what you're seeing there.
Yeah, so it looks like our gain effects are significant, so for film and non-instruction and then interaction.
Okay. So I've got, here if we take a look, here's my effective film, right? And if I go through and I take a look, here's my ANOVA table, here's my F of 30, wow, that's pretty impressive. And it looks like I do have a main effective film, okay? And then I've got a main effect of instruction, and then I've got an interaction effect that's maybe marginal, we would say, okay? Now this is an ANOVA, and this is a marginal, this is an omnibus test. Can I interpret this main effective film? Or do I need to do other things to go through and interpret that main effective film? Anything, Laura?
Generally, we wouldn't interpret the main effects if there's not.
Oh, if there's an interaction. Okay, yeah, but let's ignore the interaction for right now. Let's say I was just interested in the main effective film. Can I interpret the main effective film in this design?
No.
Well, if I wanted to, do I need post hoc or do I need follow-up tests to interpret this main effective film?
For 2 by 2, I guess you wouldn't.
Yeah, why not?
Because there's only 2 groups.
Because there's only 2 groups, right? If I got a main effective film, that's saying my film conditions are different. How many film conditions do I have? 2. How many ways can those be different? Just one way, right? So here, I could go through, and so how do I very quickly make an interpretation on this main effective film, Emilio?
I'd probably look at the script.
Yeah, I'm just gonna look at the means. Like which mean is higher, right? I look at which mean is higher, and that tells me what's going on with my main effect. I don't have to do any follow-up tests with this 2 by 2 because I've only got 2 levels of my factor. If I've got a main effective film, I just go through and take a look at my means, right? Layla, interpret for me my main effective film. What's going on in my main effective film?
Looking at the estimated marginal means, or still staying?
Don't ignore the marginal means right now. Or you could Marginal means are fine, you look at marginal means, I would go through and look at the actual observed.
That, based on the film, being presented, so the one that's meant to elicit sadness versus the one that's meant to elicit amusement, we're seeing significant difference
Yep,
in expression.
yeah, how? Like, what does that mean? Yeah, I already know that I've got a significant difference because I saw that up here. What's going on with that? How do I interpret this effective film? So, Lindy, do you have an idea? Yeah. Okay. So we just look at this sort of marginal means, or if we go back up and take a look, who's scoring higher on expression? Amusement, right? So because we've only got 2 levels of this effect, this is easy to interpret, right? This is a nice thing about it only having 2 levels to a factor, is I can go through and interpret things pretty straightforward and easily, right? This main effective film is saying that people in the amusement film are demonstrating greater levels of expressive behavior than people watching the sadness film, irrespective of whether or not we tell them to inhibit or express their emotion, right? Regardless of whatever instruction they get, this main effect is saying that people who are watching the funny film are demonstrating more expression than people who are watching the sadness film, okay? So this is important, right? These effects, if we're looking at factors with only 2 levels, this is nice because it alleviates the need to go through and do a bunch of follow-up tests, at least in terms of main effects. I just go through and I can literally report, got a main effective film, F, P, and I can say, suggesting that individuals watching the amusement film are demonstrating more greater levels of amusement than those watching the sadness film. Okay, and I would report your actual observed means because that's kind of what you observed there. But pretty straightforward. People see where we're getting this. Okay, Nick, help me out here. We also see an almost identical effect of instruction. How are we interpreting this main effect of instruction?
Individuals who are told to express their emotions are doing that at higher rate than those who are told to repose.
Perfect. And how did you figure that out?
The mean for express is higher than the mean for repose.
Exactly, right? Again, we've got 2 levels of this factor, right? We've got a main effect here, main effect of instruction, and we're saying that, okay, we've only got 2 levels, that means my conditions are different. All I gotta do is go through and take a look at my means and see which one's higher and then say, oh, well, it looks like people who we tell to inhibit emotion are demonstrating significantly less levels of expression than the people who we told to naturally express emotion, which makes some sense, right? Maybe not a groundbreaking result, but something that's important for letting me know at least that my manipulation was effective, right? That if I tell people to inhibit their expression, they're at least doing it to the greater extent than people who are just naturally watching the film, okay? And then we've got this instruction effect right here, okay? And now this is marginal. We're going to go through pretend it's not marginal. We're going to pretend that it's a real thing. But Laura, you're absolutely correct. In the presence of this interaction, the question is, do we go through and interpret those main effects? Well, maybe we do, maybe we don't. I don't know, right? It sort of depends on the research question, right? But in the presence of this interaction effect, these are no longer main effects. These are conditional effects, right? Where we would say the impact of film condition on expression ratings is dependent on instruction, or conversely, we can talk about this in terms of the impact of instruction rating on expression behavior, or instruction condition on expression is dependent on which film people watch. Okay. Now, there's some other stuff that I want you to go through and be aware of in this table here. We see a number of other lines. We see this corrected model up here. Okay. Sum of squares corrected, degrees of freedom, mean squares, and then a significance test and things like that. This is just, remember we talked about your sum of squares cells? That's SPSS is just providing that for you, okay? If you were to calculate all this by hand, this is your sum of squares cells, okay? Down here, sum of squares intercept. This is a test of your grand mean. Okay? Now the test of my grand mean is statistically significant. Haley, what do you think that means? If I'm saying the test of my grand mean is statistically significant, what does that mean?
I'm not sure, because what are you comparing that?
Well, if I see a test that's statistically significant, 99% of the time, what does that mean?
That it's different from our population,
That it's different for what's our reference value almost always?
another sample.
Not here. When we're doing our hypothesis test, what was our hypothesis test almost always different from?
That the means of each group are different, or the null would be that they're the same. It's not
Okay.
just saying that they're different.
Well, this is a test of the grand mean. Kate, do you have an idea?
0?
0, right? So if I have if my test of my grand mean is statistically significant, what does that tell me?
That there is a difference based on, wait, which condition are we looking at? Oh, it's
The grand mean.
Just that it's not 0.
Yeah, that's it, right? It's just saying that the grand mean is not 0, right? That the mean level of expression is not 0, right? Is that a useful thing to know within this data? Not really, right? 0 is not even a real value that people can have on their expression rating, right? But what I want you to go through and know, if you're looking at these output, anytime you look at an output for any type of statistical thing, you should be able to identify and know what every line on there is, right? You should be able to know, so that it's not just some mystery like, oh, I am cherry picking X, Y, and Z. I want you guys to be able to know what's this, what's this, what's this, what's this, right? So this is just your sum of squares cells. This is the test of your grand mean, which is almost always never interesting. Here's your total sum of squares. This is going to be your total, the sum of your sum of squares here with your intercept. So if you add up all your sum of squares for your effective film, instruction, and then your interaction and your error, and then add up the intercept, this is going to give yourself sum of squares total here, okay? So, but this corrected total. This is what we have been talking about to this point in terms of your total effects, right? In our calculations. So if you're looking at this, strike this corrected model, strike this intercept, and then strike this total, and now you've pared this down to the ANOVA table that we've talked about and worked with going through our hand calculations, okay? SPSS is giving you some additional information that can be important for calculating some different types of sort of subsequent analyses and things along those lines. But what we're wanting to look for, if you're looking for sum of squares components as we've put them together in the last lecture, you're looking for your effect A, effect B, your interaction, your sum of squares error here, and then your corrected total is going to be the total that we've talked about. Okay? Questions on any of that? All right, so let's go through quickly and just walk through a hand calculation because here we've got partial A squared. Someone tell me, Emilio, can you give me an interpretation of your partial A squared for film?
Not off the top.
Okay, that was a tough question. Anybody provide an interpretation of that partial A squared coefficient? Yeah.
I'm gonna try.
Yeah.
14% of the variance of expression rating is accounted for by film condition.
Okay, so you're in the ballpark. So Laura says approximately 14% of the variability in expressive behavior attributable to film condition. Okay. You've given me an interpretation, but not of an interpretation of partial A squared. What did you give me an interpretation of?
The full eta squared.
Eta squared. Yeah, right. And if I wanted to calculate eta squared from these data,
Is it that it's not already taken up by the the instruction condition. And
There we go,
interaction.
there we go. Now, if I wanted to calculate eta squared, I can do this easy, right? I can say, I can take, so let's say I want to calculate eta squared for film. I'm going to take my sum of squares for film condition, 27.487, and divide it by what? What do I divide by, Laura?
I stopped listening to write note.
Okay. So what do I, so this is my sum of squares for effect. What do I divide that by to get my eta squared? Sum of squares total, perfect, right? And Evelina, tell me what that number is.
1,052.
Oh, so you got tricked there. Remember, what sum of squares total are we wanting to work with in terms of like our ANOVA stuff? What's that?
The one for film.
Okay. Remember, what is this total represent?
Total flux.
Yeah, including this intercept. Do we care about that intercept? No. So which is the sum of, when we talk about sum of squares total, which sum of squares total are we talking about? The corrected one, right? So we want to take 27.487 divided by what? 222.2. We'll call it 88 for keyboard. What are you doing? Okay. And someone tell me what they get when we make that calculation.
Why did you learn it to 88?
Oh, it's 8.6. Oh, I'm sorry. 8.6. There we go.
0.124.
124. Perfect. Okay. So, if we then go through and take a look at our partial eta squared, what's our partial eta squared for film? What is it, Laura?
14.2.
0.142?
Yeah.
14.2, that'd be massive.
It's a good. That's good.
This is the president's back. Okay. So someone tell me, does this make sense? Does it make sense that my eta squared is smaller than my partial eta squared? Yeah. Why?
Because it removes the variance that's explained by the instruction condition.
Exactly. Okay. If you go back through and take a look at your effect size slides, this is the difference between eta squared and partial eta squared. Eta squared is nice because it has a nice intuitive meaning, right? I can say based on these data, about 12%, 12.5% of the total variability in expressive ratings is attributable to film assignment. Okay. Because we're talking about a piece of the total variability in my outcome, okay? What's the problem with eta squared within the context of our ANOVA designs, or our factorial designs?
Overestimate something.
So yeah, in general, eta squared and partial eta squared, these are positively biased estimates of the actual population parameter. They're too big, right? Because they can't be negative, right? Anything I throw there is going to capture just by random some variability. And so even if the true population value is 0, my estimated effect is never going to be 0. It's always going to be bigger than 0. So eta squared, partial eta squared are biased test statistics. They're not good estimates of a population parameter. They're fine descriptively. They're fine just saying what's going on in this data, but they're not a good population estimate. But what did we talk about? What starts to become problematic about eta squared within the context of an ANOVA design? Excellent, yes. Shoot, I'm gonna give you a high five. yeah, as we go through, we start to go through, particularly if we're working with, and this is us clinical folks, you experimental folks do a better job with this because you've got random assignment to different conditions and things along those lines, right? But for us experimental folks, we want to back, well, we're going to use an ANOVA to design. I'm going to look at a 2x2. I'm going to look at the differences in functioning across gender and PTSD diagnostic status. Well, gender and PTSD diagnostic status correlated with one another? Yep, right? And so now all of a sudden, each one of my factors is only getting just stuff that's unique to it. And so what ends up happening is as I start to layer in more factors, and even in an experimental design where everything's randomized and randomly assigned, there's still going to be some overlap, right? Just randomly, there's going to sort of this, the correlation between my factors is never going to be exactly zero. And so what ends up happening is I start adding more and more things into the mix. The numerator, my sum of squares for my one effect, starts to get chipped away, it starts to get smaller and smaller. And so on average, my eta squared is going to start to get smaller and smaller as my designs start to get bigger and bigger. And so we have a concern about our ability to compare eta squared or omega squared if we were calculating that across different designs. Our partial eta squared is better, right? Because what we're doing here is we're saying of all the stuff that's not accounted for by my other factors, what proportion of the residual variance is attributable to sort of this factor, right? So in this case, my partial eta squared here is asking, so if we take out of this total, if we suck out stuff that's due to film and the interaction of film by instruction, what proportion of whatever's left over is being attributable to my instruction condition, right? Or I guess we're looking at film condition here. So if we take out of my total, if we take out variability that's attributable to instruction and variability that's attributable to the interaction, of what's left over, what proportion of that can we assign to film condition, okay? So when we're going through and calculating it, our eta squared is sum of squares effect over sum of squares total, right? For my partial eta squared, that's sum of squares effect over sum of squares effect plus sum of squares error. Okay. So here, if I take, here's my total, but in my partial eta squared, I've got error, and what's that? What do we, sum of squares error is just our random stuff, right? That's variability we haven't accounted for. Plus, my sum of squares effect of whatever effect I'm looking at. So anything else that's gone in the model that's the variability that's been predicted, we're sucking that out, right? And so our partial eta squared is a partial coefficient, which is nice in terms of comparability, but it also makes it difficult. It complicates the interpretation, right? What I would say here, and again, go through that handout I gave you looking at effect sizes for Factorial ANOVA designs and things like that. I've sort of laid out interpretations and things like that. What I would say looking at this is I would say that film is accounting for about 14% of the residual variability in overall expressive behavior after accounting for the effect of instruction and the interaction of the film by instruction. Okay? Start to get this into your head. This is going to start to become important because as we get into regression, we're going to start talking about partial correlations and semi-partial correlations. How we're divvying up this, the denominator of these effects is going to become really important. Okay. All right. So we see eta squared and partial eta squared. Questions on this? Okay. Are we happy with these? What do you think, Evelyn? You've been on a roll of effect sizes. Are we happy with these?
Yeah.
Well, maybe. What might we not be happy about these with, for? Leila, you had touched on these too. What's our concern with eta squared and partial eta squared?
It's never going to be negative.
Okay, so it's never gonna be negative, and so it's always gonna be positive, right? So we know that these are bias test statistics, right? They're not great in terms of population effect, right? And so what do we have in our back pocket that we can calculate instead of partial omega squared, right? And so, let's go through, we'll say, omega squared is 0.124, partial eta squared, 142. Okay, so let's go through and just do a walkthrough of how we would calculate or omega squared and partial omega squared. Okay, now omega squared for these factorial designs is going to be a little bit complicated because it's going to, depending on what the design is, it's going to change the nature of your formula. You're going to keep adding other stuff into it. But what we're going to do here to calculate omega squared, what we're going to do is we're going to take, and we're going to calculate it for film. So we need to take the degrees of freedom for our effect, and this is again in the slides in the previous lecture, or excuse me, in this lecture, but stuff that we went over. So we want to take degrees of freedom for our effective film, which is going to be 1, right? Boom, right there. And we want to multiply this by our F statistic minus 1, right? Amelia, what's my F statistic for my main effective film?
30.684.
30.684 minus 1, okay? I'm going to take that over. Now what we need to do is we need to go through and take this over F statistics for all of our effects that are within the model, okay? So I'm going to start with F for my main effective film is what? 30.684 minus 1, okay? Plus, what's the main effect of my factor B? Amelia, we'll stick with you, man.
30.416.
30.416 minus 1, plus, what's the effect of my interaction?
3.488.
3.488 minus 1, okay? And then we're going to add to this my total number of people in my sample. It's going to be 189, okay? Now, if I were to have 3 factors in this, in my model, right? Let's say I have a 2 by 2 by 2. How many terms am I going to have in the denominator? For a full factorial design. How many cells do we are? So with a 2 by 2 by 2, we've got a main effective factor A, main effective factor B, main effective factor C. I've got an interaction of A and B. I've got an interaction of A and C, and then I've got a 3-way interaction, right? So I've got 5 different terms down here. Down here, if you're calculating omega squared, you have to account for all your different factors, okay? So go through, take a look at those slides and make sure that you're squared away with this. But if we run this out, we get an omega squared value of, for film, 0.118. And Haley, how does my omega squared relate to what I calculated for eta squared?
It's less biased and it assumes that the design is balanced.
Well, it does assume the design is balanced, right? But just in terms of numerical stuff, how does this relate to eta squared?
It's less.
It's smaller, right? Because we know eta squared is a positively biased statistic. And so we would expect our omega squared to always be a little bit smaller. This is a check, right? Just understanding what you're doing. If you get an omega squared that's bigger than your eta squared, you know you've screwed something up, right? Because by definition, this should be smaller, okay? So what I would do, omega squared is still positively biased. It's just less positively biased than eta squared, right? And so for eta squared, I would say within these data, it appears about 12.4% of the variability in expression ratings is attributable to film condition, right? So I'm saying in these data. Here, if I were going to go through and interpret my omega squared, I would say based on the data that we've collected, we expect approximately close to 12% of the variability in expressive behavior to be accounted for by film. About 12% of variability in expressive behavior in the population attributable to film condition or something like that. Okay, this is a population statistic. It's biased, but it's a population statistic. This is a descriptive statistic for the data that you're working in. Okay. All right. So let's go through and calculate now partial omega squared. Partial omega squared actually easier than omega squared with these factorial designs. With partial omega squared, I'm just going to take the same numerator, degrees of freedom of effect times my f value minus 1. So we're going to have the same numerator, 1 times 30.684 minus 1 over, now what we're going to do is we're going to take degrees of freedom of effect, which is 1 times the effect I'm looking at, or the f value, which is 30.684 minus 1, and then now I'm just going to add my sample size, 189. Okay. So I get a partial omega squared of 1.136. Okay. Again, Emilio, how does my partial omega squared relate to my partial eta squared?
It's going to be smaller.
It is smaller, right? Again, suggesting that we've got a correction for positive bias of my eta squared statistics. And once again, if I'm interpreting my partial eta squared of 0.142, I'm going to say within these data, film condition accounts for approximately 14% of the residual variability after accounting for instruction condition and the interaction of film by instruction, right? If I'm making an interpretation of my own partial omega squared, I was going to say based on these data, based on the data that we've collected, we would expect approximately 13.6% of the variability of expressive behavior in the population to be attributable to film condition, right? So this is a little bit weird because we're working in the context of an experiment, right? Like it assumes that we've taken everybody in the universe and had them sort of shown them either a sad film or a funny film and then watched them express their behavior. But it's important to think about conceptually what's going on with some of these outcomes here. Okay. All right. Questions on our omnibus stuff? Feeling okay with this? This can get kind of tricky and kind of heady. People feeling all right with this? Okay, cool. So, we've got now some main effects, but it looks like we might have an interaction, right? Our main effects we can, within this design, we can interpret fairly easily because there's only 2 levels. That's not always going to be the case. And then we've got this marginal interaction that may or may not be something that we want to take a look at, right? And so we have to go through and think about how do we go through with these designs and start to take a look at some of these more complex effects. Okay. So, let's say we have an interaction or some sort of main effect that needs followed up on. How do we go through and do this? Main effects are fairly straightforward. We'll talk about those. Interaction effects can be a little bit tricky, okay? But if I have an interaction, right, which is oftentimes why we're running these analyses in the first place, right? We want to see whether or not this factor influences the nature of the impact of this other factor on our outcome, right? And so again, if I have an interaction, it's just saying that the effective factor A on our outcome is dependent on factor B, or the effect of factor B on our outcome is dependent on A. Mathematically interchangeable, you can go either way, right? But we need some more follow-up tests to go through and start to figure out exactly what's going on. Remember, we had worked on our in-class example, looking at the impact of temperature and humidity on some sort of test performance. We have, what's the design of our study here? Laura? This is 2x3, right? We've got task difficulty, or I guess no, this isn't temperature and humidity. This is task difficulty and arousal. There we go, right? So we've got people completing hard tasks and people completing easy tasks, and then we have people at low, medium, and high levels of arousal, right? And so if we plot this out, which we should always do, again, if you find an interaction effect, always plot it out first. How do we go through and tackle this? Well, there are a couple different ways. We have a couple different options for going through. We can go through and use our planned contrasts, right? This is us a priori saying, these are the conditions, these are the things that I want to go through and test. There are many different things that I could work through. These are the ones that I'm going to choose to work through. And then we've got some post hoc tests. Post hoc tests seem easy because I'm like, oh, I'm just going to evaluate all pairwise comparisons. This actually gets very tricky to do within the context of a factorial design, because not all of your comparisons are going to be interpretable here, and you need to go through and see how many interpretable effects that you're working with. Okay. Other thing that you need to do when you're teasing apart these interactions, have to think about what makes sense from the perspective of theory, conceptualization, things along these lines, right? Because I could approach this interaction in two different ways. John, how do I know that this is an interaction effect, by the way, just looking at it?
Because as like if you would like draw lines from like the top of each, like easy and difficult, it would be parallel.
Yeah, exactly. And it looks like the differences I'm seeing here are sort of not the same across all things. If I draw a line, I've got one line going up, another line going sort of like a V, upside down V. They're not parallel lines. I can tell that this is an interaction effect, right? Now there's a couple different ways conceptually I can go through and try and approach this. I could ask myself, what's the effect of arousal at performance at different levels of task difficulty, right? Or I can say, what's the effect of task difficulty on performance at different levels of arousal, right? Again, these are mathematically equivalent. It doesn't matter which way I go through and do this. I could do either one, but they may not be conceptually the same thing. Oftentimes when we're working with these interaction effects, we start with some baseline effects or some baseline difference, right? I know that there are gender differences in depression, okay? That's something I know, right? It's not, if I demonstrate that, that's not news. Everybody knows that, we've known that for a long time. But maybe I'm interested in knowing whether or not there's anything else that starts to impact that gender difference. Maybe in some groups, the gender difference is quite big, and maybe in other groups, the gender difference isn't large at all, right? Maybe I'm looking at doing some cross-cultural research, and I'm looking across different Western industrialized nations, whether or not that gender difference depends on whether or not we're talking about sort of X, Y, or Z, right? So then maybe my question is, does gender differences in depression depend on country of origin, right? So I could also ask, does country of origin, differences in depression in country of origin depend on gender? That seems like a less interesting, or that doesn't make as much sense. I don't know if I have existing reason to expect differences in gender, or differences in depression across countries, kind of, then it starts to get more convoluted. I mean, the question makes more sense one way than the other, right? And so you want to go through, be thinking about what's the best way to go through and approach this, what makes conceptual sense. Do this before you start jumping in and trying to tease apart different differences and things, okay? So, if we're going through and taking a look at this, how many meaningful different pairwise comparisons can we make with this? So I want to take a crack. John, what do you think, man?
Six. Maybe 2 by 3.
Okay. Maybe, right? How many? So we've got six different cells, right? And if this was a one-way ANOVA, how many meaningful comparisons could we make? Or I guess how many possible pairwise comparisons can we make with 6 means? Anyone remember how to shortcut in calculating this? So we got 6 means. So if we go so we take my number of means times the number of means minus 1 over 2. This gives me my possible pairwise comparison. So with 6 means, how many possible pairwise comparisons could I make? 15, right? There's 15 possible pairwise comparisons that I could make based on these data. But the problem is that all of these comparisons aren't going to necessarily going to be meaningful. Okay? So if I take a look at this, I've got a simple main effect of factor A at every level of factor B. Okay? So with factor, so I say, what is the effective task difficulty at low levels of arousal? Okay? So factor A is task difficulty, easy, hard, and factor B is arousal level. I've got 3 different comparisons that I can make here. I can say, what's the effective task difficulty on performance at low levels of arousal? Effective task difficulty at medium levels of arousal? Effective task difficulties at high levels of arousal. So I've got 3 comparisons here that I can make, right? What I'm doing is I'm looking at the effective factor A at every level of factor B. Are people comfortable with this? Okay. I could also ask, what's the main effect, or what's the effective factor B at each level of factor A, right? So you say, what's the effect of arousal on performance for easy tasks, right? So if I'm just looking at easy tasks, I've got sort of this comparison here, right? Under what levels of arousal does performance differ, right? So here, within this, if I'm looking at the effect of arousal on performance for easy tasks, how many pairwise comparisons do I have here? Haley? 3, yeah. I can go low versus medium versus high, medium versus high. Okay. Then I can ask, what's the effect of arousal on performance for difficult tasks? Right? If I'm looking at difficult tasks, I can look at low, high, medium, high. Okay. How many total possible how many pairwise comparisons then am I looking at based on this 2x3 interaction? How many, Amelia? 9. Is 9 15? No, right? Because there's effects here that don't make sense to ask, right? Does it make sense to compare performance in low arousal difficult tasks with easy high arousal tasks? I don't know what to make of that. There's that maybe I can see there's a difference, right? But I don't know what to make of that, right? Because I've crossed factors, I've crossed levels. This is an apples and oranges comparison, right? I could look at performance at difficult tasks at medium levels of arousal with easy tasks at low levels of arousal, but that comparison doesn't make sense because it's an apples and oranges thing, right? I can look at within each level of factor B, or of factor B here, I can look at the impact of arousal across task difficulty. I can look at this, I can look at this, I can look at this, right? Or within easy tasks, I can compare things, or within hard tasks, I can compare these. But this is what starts to happen when you got this factorial design. All possible pairwise comparisons aren't meaningful. I mean, no one's going to kick down your door and arrest you if you try and run them. You're just going to have a number that doesn't make any sense. There's no way to interpret it, right? There's no meaningful comparison that you can make with this stuff. And this starts to become important when you're going through and starting to attack these interaction effects. How am I going to go through and look at this, right? And oftentimes, if you're going to look at all meaningful pairwise comparisons, that's just a whole lot of stuff that you're going to be going through and looking with, which starts to become problematic within the context of some of your post hoc approaches. Okay. People sort of understanding, kind of seeing what we're doing here? Okay. So what I might do then, right, let's say that I'm interested in looking at simple main effect here, effective factor A at every level of factor B, right? I'm just wanting to go through, boom, 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 these are the tests I'm gonna make, right? I'm just basically gonna do 3 t-tests, looking at differences here, looking at differences. That's the whole reason I went through and did this. Or maybe I'm actually more interested in qualifying this through this simple main effect, effective factor B at every levels of factor A, right? What I might do here is I might split this file by task difficulty, and then what might I do to see if there's anything going on in here. So if I split this by task difficulty, now I've got 3 levels of my factor. What might I do to sort of see if there's anything there, and maybe start to rule out whether or not I need to move forward? What analyses could I do? What do you think, Haley? There's a post hoc, it's kind of a post hoc, but what specific, if I had 3 means that I wanted to see were different, what would I run?
Just a one-way ANOVA?
Yeah, I just run, I split this by file, and look at a one-way ANOVA. And then if I see, maybe I see differences here, but when I split it by difficult task, my one-way ANOVA is not significant. Then I say, okay, well, so these means aren't different from one another. What I'm gonna do is I'm gonna focus on this stuff, right? So the idea is you wanna have some sort of plan, some sort of way to approach this that makes sense within the context of your research question, so that you're not running 9 different tests and then having to explain 9 different tests. Because if you run a test, you better be ready to talk about it. And so if no one wants to talk about comparisons that don't make any sense, right? If I say, Nick, here, why don't you take a look at sort of this group and that group? You're like, well, I could. I don't know what I would make of that because there's no reason to compare those groups. Well, I'm going to want you to go through and run it, include it in your study anyway. Well, I can do that, but God help me if it turns up significant, because now I got to talk about it, and I don't know what to make of it because that wasn't the reason I did this study in the first place, right? So again, this idea, particularly with these factorial designs, you really want to have a good sense for why am I doing this? What do I expect is going to happen? And if I get these interaction effects, how am I going to go through and test this in a way that's reasonable? Okay. So one thing we can do is we can use our linear contrasts. Again, this is going to be no different than the linear contrasts that we ran in our last assignment. Again, there's a classic approach using your f-tests and things along those lines, but those actually get kind of bulky in terms of calculating, making everything sort of be on the same page in terms of standard errors and calculating confidence intervals and things along those lines. So again, just use the same formula that SPSS is using. We've got our t-statistic is our value of our contrast over our standard error of the contrast. Standard error of the contrast is the mean squared error times the sum of your squared weight over the individual cell sizes. Now note that your mean squared error here, I'm going to recommend that you take that mean squared error estimate from your simple effects ANOVA table, okay? So if I want to go through and I want to compare within the context of difficult, a difficult task, and I think that my a priori hypothesis is that performance is higher at medium levels of arousal is composed of low and high if we're talking about difficult levels. What I'm probably going to do is I'm going to split this up. I'm going to split the file by task difficulty. I'm going to run a one-way ANOVA, and this is going to be my simple effects ANOVA right here. And then what I'm going to do is I'm going to take my mean squared error from that as opposed to taking the mean squared error from the overall thing. This starts to become tricky. There's a lot of different ways to do this. I'm giving you one way to do it. There are other ways to do it, more sophisticated ways to do this. But again, if we had a whole nother class where we could just walk through ways to go through and sort of pull apart sums of squares and stuff like that, that would be kind of cool. We don't. So we're going to do it this way here, but if you find another way, a different approach, sort of be aware that there are lots of different ways to tease this apart. Okay? So we've taken mean squared error from our simple effects ANOVA. Our T critical is going to be our T for our alpha with our degrees of freedom taken from our mean squared error here. Here's our confidence intervals. You also have SPSS. We'll go through and make corrections for standard errors, correction to your standard errors and degrees of freedom for violations of homogeneity of variance. Again, I've done some looking into the actual how they calculate this, and there's not a lot of. SPSS says this is a valid, suggests or implies that this is a valid test for violations of homogeneity of variance within the context of calculating contrasts. I don't know that that's necessarily true. It's an old paper from like the 60s that no one else seems to ever cite ever, so take this with a grain of salt. But a different approach that should be used here. Okay. So we're talking about simple main effects. Okay. So this is when we're getting into our interaction terms, starting to tease things apart. We also run into some issues if we're looking at our effect sizes for our simple main effects in our factorial design. Again, we're still going to calculate these as the value of our contrast over some standard deviation error estimate. But what starts to become difficult here is deciding what that standard deviation estimate should look like. Okay? So again, if we think about our design looking at cast performance across different humidity and temperature conditions, right? In our one-way ANOVA, our mean squared error is pulling in variability that's not systematically related to temperature, right? So if I'm just looking at one-way ANOVA across, I guess, okay, so this is not including, okay, yeah, this would be humidity. So if I run an ANOVA looking at impact of performance across my two temperature conditions, I'm going to get a mean squared error, right? And that mean squared error is going to be variability, or excuse me, sorry about this, if I look at temperature, right? I use a one-way ANOVA design to look at mean differences across 50, 70, and 90 degrees, right? And I just run this in my one-way ANOVA. My mean squared error, that's going to be all the variability that I'm seeing in my performance scores that's not related to temperature, because temperature, that's going into my mean squared effect, right? So here I've got my total variability in my one-way design. We've got temperature here, and then everything else gets dumped down into my error. Okay, people follow me at this point? Sorry, I screwed that up in trying to explain this, but all right. For my 2x3, remember we're starting to go through and we're going to starting to add in additional factors. So we have other systematic things that might be accounting for variability. So my 2x3, my mean squared error for my 2x3 factorial design contains variability not systematically related to temperature, humidity, or the interaction. Okay? So if I'm looking at these two designs, which one of these designs, Haley, is going to have the smaller error term? This one where I'm just modeling in temperature, or this one where I'm modeling in temperature and humidity and the potential interaction?
The bigger one,
The bigger one, why?
because you're counting for more of the.
Yeah, because I'm accounting for more stuff. In this design, there's variability here in my error term that could be modeled that's due to temperature, humidity, and the interaction. But all we're doing is we're just pulling out temperature. And so what ends up happening is my error term ends up being bigger here than here. Okay? Now what ends up happening is because my mean squared error is systematically lower in my factorial design, what does that end up doing to my tests of effect? If I'm, for my pairwise test, if I'm just going to go through, remember, because one of the things we can do is with our one-way design, we can say, well, if you have equal sample size and you haven't violated homogeneity of variance, we can just pull that mean squared error term, take the square root of that, and that's going to be your standardizer. That's a fair thing to do. Okay. If I do that with my, do the same thing in my factorial design, what's going to happen to my effect size?
Wait, sorry, your effect size or test statistic?
Well, both. What's going to happen to that effect size, Kate? You know,
Go up.
it's going to get bigger, right? Because I'm dividing it by a smaller error term, right? So what I might be interested is I want to go and I'm doing a pairwise comparison. I want to calculate effect size comparing performance in temperature at 50 degrees and 90 degrees, right? That's the pairwise comparison I want to do. If I got my total, if I'm looking at in a one-way design, right? I'm just pulling out my mean squared error accounts for all the variability that's not attributable to temperature, right? And the variability in performance across 50, 70, and 90 degrees is all about the same. I haven't violated homogeneity of variance. That mean squared error term is a nice, it's just a pooled variance estimate, right? And so that's a nice thing to use. But in my factorial design, now all of a sudden, that error term is smaller, right? Because what I've done is I've pulled out temperature, humidity, and the interaction of temperature and humidity. Now, the effect size I want to look at has nothing to do with humidity. It has nothing to do with the interaction. It's just looking at whether or not people in the 50-degree condition are performing higher than the 90-degree condition, right? But if I just pull my mean squared error term out as my standardizer, that's going to jack my effect size up, because what I'm doing is I'm pulled out a bunch of variability that's not involved or doesn't have anything to do with the thing that I'm actually looking at here, right? And so the concern ends up being that what happens is if we just go through and start pulling error terms out of our ANOVA table, we start to get inflated inflated effect sizes. And why are we worried about inflated effect sizes? What's that?
Type 1 error?
Well, potentially. Why do we have a goddamn replication crisis on our hands?
Because people only report big effect sizes.
Yeah, because we only report studies that have big effect sizes, because those are the studies that are most likely to claim statistical significance. And if I only get to publish things that are statistically significant, if this is my distribution of possible effect sizes I might get in a study, here's the true population value. These are all the studies I'm publishing, right? Because they've already all wildly overestimated my effect size. And now, if within that design, now I'm using things that are inflating that even more, either with my eta squareds, either with it sort of these. It just makes that effect size super huge, right? So I'm like, oh, I'm going to replicate Evelina's study with 30 people because her effect size is 1 billion, and no one can ever do it, right? And we say, oh, Evelina's research is garbage because no one can replicate it. Like, well, you could, and it may be not that it's not an effect. It's just you need a lot of people to replicate it, because that effect actually isn't here. That effect is down here, right? It's a real thing. You just need to have about 75, 100 people per cell if you're going to actually replicate that effect that's in the population, right? Now, maybe you say that's no longer a meaningful effect because it's too small or not, but just the way we work our statistics is why we have problems replicating this stuff. It's not necessarily anything that you did. It's not necessarily malfeasance on your part. It's just we systematically go through and we cherry pick the stuff that's a wild overestimate of our effects anyway. We publish those, and then everything else doesn't get published, and so then we think that this is the effect we're looking for when it's not, right? We're hunting something completely different, okay? So we want to be careful of this. So Howell recommends a procedure for calculating effect size. And so again, this would be a situation where we would be in a fairly balanced design, where we're going to say our D, calculate our D as the value of our contrast over some estimate of error, right? And what Howell suggests is, let's say, all right, what I want to do is I want to calculate my effect size for a linear contrast looking at involving temperature, okay? And so what I'm going to do for my standard deviation, my standardizer term here, what I'm going to do is I'm going to take the sum of squares error, because that's everything that's left over, plus the sum of squares humidity, because my contrast doesn't involve humidity, plus the sum of squares associated with my interaction, because my contrast doesn't involve the interaction, and then I'm going to divide that by the degrees of freedom error, degrees of freedom humidity, and the degrees of freedom by that interaction. Basically what I've done is I've constructed a standardizer specifically for this effect size that's going through and basically including everything, all the variability in my outcome that doesn't specifically relate to the effect of interest, okay? And so what you're going to get here is a much more conservative, because, I mean, just look at it. If I take the square root of my mean squared error, right, which is sum squared error divided by my degrees of freedom, we get a much, much larger effect size than if I'm accounting for variability that's attributable to the interaction and variability that's attributable to humidity, right? Again, the concern is that if we just go through and just start pulling this error term, we're starting to systematically inflate our effect. Whereas if we were to go through and we were to look at this contrast in a one-way design, just looking at differences across temperature, that mean squared error would be much, much larger, right? So in terms of thinking about what's the effect of temperature on performance and calculating effects there, want to be careful about how we go through and choose our standardizer, okay? So looking at our effect sizes, again, it's always going to follow the same form. It's going to be some, who's calling this pitchfork coefficient or something like that? That's pretty high. I like pitchfork coefficient. So evaluate contrast over some estimator. Estimator given square root of your mean squared error from your factorial ANOVA. Don't do that. That's just, don't. It'll give you an effect size that you like, but it's not going to be something that's meaningful or comparable. What you could use is the square root of the mean squared error from your simple effects ANOVA, right? Here what we could do is we could look at, if this interaction we're looking at impact of temperature across levels of humidity, right? We split file by humidity and then just run a one-way ANOVA for temperature and high humidity, one-way ANOVA for low humidity, and then I'm just looking at differences in humidity across with this. Then maybe mean squared error from that simple effects ANOVA would be useful. But again, we're assuming a balanced design, no violations of homogeneity of variance. Okay? Or maybe what we do is we go through and we use the square root of the pooled variances of our sample in question. Right? If we're worried about unequal cells, violations of homogeneity of variance, what we're just doing is we're creating our own error or variance estimate that's just looking at including the variance that's included in the test that I'm looking at. We modify our pooled variance estimate, but that's just sort of adding some additional terms in there. It's not a big deal, okay? Or we can have a standard deviation of the control group is also, so the glasses delta, and just use that as to calculate our contrast, okay? So again, you can start to see, hopefully, like why effect sizes haven't just taken hold, right? It's not just a p-value. When you calculate a p-value, it's all the same, right? What goes into calculating your effect size depends a lot on your conceptualization, what the data is doing. There's just 1,000 different variables to go through and think about, consider, which makes it harder and then people don't do it, right? Or if they do it, they're back, oh, my effect size D is this, right? Anytime I see that, I'm like, well, that tells me nothing, because I don't know how you calculate it. There's like 15,000 different ways you could have done that. I'm assuming, because I'm cynical, that you just chose the one that gives you the highest effect size, or the one that you learned in your stat class on a sheet, and then just went forward with that, even though that doesn't make sense, right? So when we're thinking about reporting our effect sizes, this is why I ask you guys in these assignments to not only calculate, in fact, tell me how you calculated it, and then give me a justification for why you calculated it, or used the approach that you did. Okay? All right, so thinking about how we go through and tease out how to go through and decide on our contrast. If we're thinking about, okay, I want to calculate a contrast, if I have a balanced design with no clear violation of homogeneity of variance, maybe I could use a factor, or use my mean squared error from my factorial ANOVA, but probably not. Right? There's just too much stuff going on. It's too problematic. If you got a perfect design, perfectly balanced design, variability doesn't look bad, everything looks the same, then cool, go ahead and do that. But in real applied research, that usually doesn't happen. Usually what you're thinking about, if you've got unbalanced designs, possibility of violations of homogeneity of variance, this is going to be your more conservative option. Okay. Calculating effect sizes, how do I go through and calculate, or what do I use as my standardizer for my effect sizes? Again, no concerns regarding reporting a D statistic that's way too big. Maybe pull your mean square, the square root of your mean squared error out of your factorial ANOVA. Don't do that. But if I got a balanced design, no clear violations of homogeneity variance, maybe I'm looking at this simple effects ANOVA table, unbalanced design, possible homogeneity variance violations, just go through and pull the variance of your target cells, or you got glasses delta, if you got a nice baseline comparison, go through and use that. Okay. Questions on this? All right, cool. Let's take a break. Let's take 5-ish on this, and we'll come back and a couple different examples. So we've got, in this situation, a marginal interaction of film by instruction, okay? So Emilio, tell me, I say, hey Emilio, I ran this study and I got an interaction of film by instruction. Interpret that for me. And that's all you know. What do you say?
At some point, there's a difference between two of the cells. So, between two of the combinations of the film conditions and the instruction conditions.
Okay. That's getting at it, but I'm confused because that's a lot of words and I'm having a hard time following it. How could I say I've got an interaction of film and instruction? Someone could tell me, like, what is an entirely accurate interpretation of that interaction? What would I say?
The influence of film on expression writing depends on instruction.
Yeah, now I didn't tell you what I was looking at, but you're exactly right. The effect of film depends on instruction, right? Like that, very simply, like that is the interpretation of any interaction that you'll ever encounter ever in the universe. The effect of X on Y depends on M, right? That's it. Like I don't have to know what you're measuring, how you measured it, what the outcome is. Say the effect of film depends on instruction, or the effect of instruction depends on film, right? That's all you need to do, and then, like just having that down as basis will be helpful in terms of thinking about some of these interaction effects. But let's say then that we're going to say that this interaction effect is worth looking into. Let's pretend that we're not super tied up with it being exactly a p equal 0.05, and we're going to say, all right, so this is worth exploring more. What's the first thing I do? Anytime you get an interaction effect, what do you do first? Graph it, absolutely. Never skip this step, all right? I like going through, Excel is a nice way to go through and graph this stuff, okay? What I've done here is I've got, put together a small table. I've got express, withhold, sadness, amusement, and then I just went through and plugged in my observed means for each one of these, okay? And if we do that, and you go through and you graph this out, note that if you go through, select this, and then graph this thing, what am I looking at? Insert. Here we go. So this switch column and row. This is going to be important. No, because I can't ever figure out which way Excel is going to graph it. But you want to make sure that your graph makes sense in terms of how you're going to think about this, right? So remember, what was our expectation going into this analysis? We had said that the inhibition impacts the expression of amusement to a greater degree than sadness, right? So if I'm going to plot this out, I am probably going to do it. Does it make sense to look at it this way? I mean, yeah, I guess. But if I'm saying, looking at the effect of instruction condition, express, withhold, at each level of my film condition, I have to kind of jump across. I have to jump across to get that comparison that I'm actually interested in, right? If I flip it around, I switch it that way, then that's pretty easy to see, right? My expectation, my hypothesis is that the impact of inhibition is going to be more prominent for people exposed to an amusing film than a sadness eliciting film. And so here, I can see that, right? I'm just looking at my effect of instruction condition at each level of my film condition, right? So people see kind of how switching that graph around makes that easier and more apparent than not. I mean, you can do it either way, but just being mindful of setting this up in a way that makes sense. To the greatest extent that you can do this in a way that's intuitively meaningful and you go through and make some sense of it, this is going to help you from getting confused and turned around, okay? So what I'm wanting to do, my expectation, and so the whole reason I did this is I think that telling you to inhibit your emotion, I think you're going to be more successful at inhibiting, or we're going to see a greater impact of expressive inhibition if we're in a situation where you're exposed to a humorous stimuli than if you're exposed to a sadness eliciting stimuli, right? So what, Evelina, what comparisons do I need to do to test that?
Post-hoc comparisons?
What's that?
Post-hoc comparisons?
Well, I'm kind of calling it a shot, right? I don't necessarily need to do a post. So if I'm saying that the impact of expression on, the impact of regulation on expression is going to be more prominent for amusing eliciting stimuli than sadness eliciting stimuli, what comparisons should I conduct to test that?
In terms of like what statistical test?
No. Which means am I going to compare up here?
Express sadness to express amusement and then sadness to amusement.
Yeah, right. I'm just going to compare these two and compare these two. What other two comparisons could I make, Lila?
Between amusement and sadness.
Yeah, which ones?
Expressive.
Yeah, right. So really, if I'm expecting that the effect of inhibition is going to be larger for amusement eliciting stimuli, for sadness eliciting stimuli, and just test these two. Right now, I can test whether or not I see differences in expression across people who are watching the sadness film who were told to express and inhibit, and people who were told to, and watching the amusement film who were told to express and inhibit. I can do that. That's fair. That's an interpretable thing I can do. Am I excited about that comparison? Is that an interesting comparison? What do you think, Nick?
Could be. To compare the express between the two benefits, is that?
Not the film clips, that's what I'm interested in. I'm saying, so I've got people who watch sadness film. Some people I told them to express, some people I told them to inhibit. Is that an interesting thing to I see more expressive behavior in people who I told to inhibit versus those who I told to express?
No, because that's kind of what people expect.
Yeah, I mean, it's kind of self-evident, right? Like if I find a significant difference, like at best, it's a fine manipulation check, but I'm not gonna publish that. Like, hey, I told people not to express emotion and they didn't, or they expressed it to a lesser degree than people who I told to just express whatever, right? I mean, I can run those analyses, but it's not necessarily interesting or useful for anything, and it's not why I did the whole thing, right? So here, there are 4 different comparisons that I could make. I can compare the impact of instruction condition for people who watch the sadness film and the amusement film, and I could look at 4 people who were told to express and people who were told to inhibit. I can sort of look at some of these, or I can see, excuse me, I'm sorry, I got that turned around. Do people who are told to express emotion, do we see more expression in sadness or in amusement than sadness? Okay, well, but that's not my research question. And for people who I told to withhold, do I see people who are exposed to amusement eliciting stimuli expressing more than sadness? Well, I can look at that, but that's not really sort of why I should have put this together in the first place, right? My interest is saying, does film condition impact the, or influence the effect of withholding emotion or express withhold on my expression condition, right? And so what I'm going to do is I'm going to look at this, and I'm going to look at this, and then I'm going to call it good, right? Because that answers my research question, okay? People kind of see how we've gone through and put this together. So what you want to do when you graph this out is you want to ask yourself, what am I looking at? Like, one, what are the comparisons I can make, and then sort of what makes the most sense given my research question. So again, I could look at the impact of expression, or excuse me, the impact of instruction for people watching sadness and amusement. That kind of gets at what I'm looking at, right? That gets at my question. I could also look at whether or not people were watching, whether film condition impacts expressive behavior for people watching, for people who are told to express emotion and not express emotion. But that deal really doesn't, that question doesn't have really anything to do with sort of what I'm interested in asking about. Okay. People kind of see sort of the approach here? Okay, so 4 comparisons that we could make. How many comparisons are we actually going to make? 2, right? 1, 2, that gets at our stuff. So what I'm going to do is I'm going to go back to my data here. And so what I'm going to do, remember that we, in these analyses, we have some problems. We do have a fairly balanced design, but we've got some problems with violation of homogeneity of variance, right? And so am I super excited about just pulling error terms from my factorial table and just starting to use that as an error term? Probably, right? Because I don't know that that's a good, I don't know what cell is different than which cell, and just using that as a global term could end up overestimating or underestimating stuff that I would need, that I'd be interested in looking at. So what I'm going to do, after looking at this, I'm just going to go and I'm going to say, all right, I want to look at the impact of instruction condition on expression at each levels of my film. So I'm going to go to data, I'm going to go split file, and I'm going to split file by film condition. And then what I'm going to do, because I've got a violation of homogeneity of variance, I'm not going to worry about, even though these are planned contrasts, I'm not going to go through and actually run a contrast because I don't need to, because it's just a pairwise test. What I'm going to do is I'm going to go in and I'm going to go to Analyze, Compare Means, Independent Sample T-Test, and I'm going to look at Instruction Condition 0, 1 on expression rating. Okay. So what I've got, my question here is, I think, my hypothesis is that I'm going to see a bigger impact of expressive inhibition in individuals watching a humorous film than among individuals watching a sadness film. And so what I'm going to do then is I'm going to go through, then I'm going to split my file by film condition, because I wanted, so I'm saying that this effect is going to be larger for people watching this film than that film. And then how many levels to my instruction factor do I have? 2. So I can just run a t-test and take a look at that stuff there. Okay? So if I go through and I do this, sort, run this, run my analyses. So SPSS has split people into sadness film, people watching the sadness film, and people watching the amusement film. All right. And Layla, what am I seeing here? What's going on for people in my watching my sadness film?
Assuming equal variances.
Okay. Do I assume equal variances in this? Why not?
Because we have different sample size.
Okay, sample size doesn't necessarily impact variance. What am I looking at to determine whether or not I'm assuming equal variances here?
The homogeneity.
Yeah, my Levine's test. My Levine's test of equality of variances. And is this this is statistically significant? What does that mean?
That means that they're
that they're reliably, that the difference isn't zero, right? So if I go through and I take a look at that, what am I concluding about levels of expressive behavior on people who were told to inhibit versus those who were allowed to express among people watching this sadness film? Do you have a reliable effect? Yeah. And so, and how do I interpret that effect?
Well, I know there's a difference, but,
So how many levels do we have?
two.
So how many different ways could this be different? Technically, it could be two. How many ways is it different? How do I determine which one is higher than the other one?
Looking at, the mean difference.
Yeah. So who's expressing more emotion?
Those who are asked to express.
Yeah, those who are allowed to express, right? So if we go through, we take a look at the Levine's test. Levine's test says we've got a violation of homogeneity variance. So we drop down here. We say, okay, equal variance is not assumed. Here's my test statistic. Here's my p-value. Statistically significant, mean difference, confidence levels, things like that. But I go through and I look and I say, okay, for individuals who are viewing the sadness film, those individuals who are allowed to expressing more, displaying more expression than people who are instructed to inhibit. Like, okay, so if I go back to my, right, so this is the comparison we're making right here, right? And we would say, based on our follow-up test, that we have a reliable difference here. This is a significant difference here, okay? So let's go take a look at our other conditions. So down here, for amusement condition, Haley, what do we got going on here?
No violation.
We have no violation of homogeneity variance, okay.
It looks like there's still a significant difference, and for amusement, people asked to express, they express more than people who are asked to hold.
Okay, cool. So again, and we're starting to see, this is why it's important, why we shouldn't just start grabbing error terms from our overall ANOVA table, because when we're talking about people who were watching the amusement film, we didn't have violation of homogeneity variance. That was fine. But if we're looking at people who watch the sadness film, there we do have a violation of homogeneity variance, right? So we start needing to pay attention to this violation of homogeneity variance in terms of how we go through and approach our test. So here we have a statistically significant effect. Here we have a statistically significant effect. And so what do we make of our hypotheses, right? So we said that we're expecting that the inhibition is going to impact the expression of emotion to a greater degree in individuals watching an amusement film versus a sadness film. Laura, which one of these conditions did we find significant differences in? Both of them, right? So what conclusions do we make about our hypotheses here? Are we happy with this? Or are we indifferent? Have we gotten a good gauge of sort of our research question down here? What do you think, John?
I would say no.
Not quite, right? So we know, if we just look at this, we can say, well, I see this looks like a bigger difference than this. But if I run my statistical test, I see we have this difference is the same, or this is statistically significant, that's statistically significant. But all the statistical significance test is just telling us whether or not something's different than zero, right? So yeah, these two are different, these two are different. What might I do to go through and augment this to try and put a little more flesh on the bones here? What do you think, Nick?
You could just just look at the mean difference.
I could look at the mean difference. What would be a better way to look at it?
Basically, yeah, right,
What do we spend a whole lot of time calculating this semester? What's up?
Pooled variance.
Pooled variance, and why do we calculate pooled variance? What is it in the service of calculating what? Effect sizes, right? So what I might do with this is, so I've gone through and I've said, okay, these are both statistically reliably different, right? Okay, my question is, I really think that this is different than this, right? And the fact that my interaction term is significant suggests that the differences are different across so just looking at the interaction term says that the difference across these things sort of vary. Now that interaction term could also be sort of the difference between sort of this thing here, right? It's really hard to sort of say definitively, but what I might do is I might go through, calculate my, calculate an effect size for this difference here and for this difference here, okay? And if I do that, let me see. All right. So here, I'm going to say for SAD, right? My pooled variance is going to be 47 minus 1 times, what's my variance here? What's 1.042 squared? What is it? 1.08. What? So give me three decimals. 1.086.
Yes.
Okay. Plus 44 minus 1. What's my variance for my second one? 0.589 squared. 347. Okay. All of this is over. We got 47 plus 44 minus 2. Someone tell me what my pooled variance is. Are we good? If you're not calculating something right now, you should be.
1.006.
What is it?
1.006.
1.006. Okay. It is, and that's pooled variance. Okay. And so what do we get for G? So we got 0.503, and we get that from our output divided by the square root of 1.006. What's our effect size? Yep. So we see that was a mean difference. Pull that from our table. 0.49. Is that what we got?
No, I got 1.586.
1.586 seems big. Did I not bring my calculator?
It's sitting right there.
Oh, okay. So you got 0.503. Yeah, so I got 0.50. So we take 0.503 divided by the square root of 1.006. Yeah, about 0.50.
Because I said 0.1006.
Oh, 0.10. Whoops.
That's right.
This is right?
The variance? Oh, just kidding.
The
Your
pool variance you have before is correct, yeah.
Okay,
Yes.
okay, pooled variance here, 1.006. All right, does that match up with everybody's stuff? All right, now let's go through and calculate our effect size for,
What was G again? We can't see.
oh, okay, we got, 0.50. Okay, so we'll put it on here so you guys can see. So here my pooled variance is now gonna be, for my next condition, is gonna be 47 minus 1 times, what's the square of 1.073?
Square root,
No, the square.
1.151.
1.151 plus 51 minus 1 times, and the square of 0.979? 0.958, all over 47 plus 51 minus 2. All right. Ninety-six, 1.050. Is that what people got for variance? Is that right? Okay. And so then G gonna be equal to 1.018 over square root of 1.050 at 0.99. Okay. All right. So, statistically significant effects here and here, right? And we can eyeball it and say, yeah, it looks like this is a bigger difference than this, right? But there's no error bars on here. We don't know about variability and stuff like that. What we can do is we can go through and calculate a standardized effect. And we see our effect size for this difference is about 0.5, about, this is twice the effect size is this, right? And we could do, if we wanted to, we could go through, calculate confidence intervals around those effect sizes and look at this just in order to gauge the magnitude. But if I go through and implement my effect sizes in here, I can now go through and say, you know what? Yeah, so these are both statistically significant, right? We see that 4 people intended, if I tell people to inhibit their expression, right? They show less expressive behavior, but that decrease looks to be more prominent in people who are shown an amusing film than those people who are shown a sadness film. Okay, and then I'm saying, okay, and that difference is about the difference of by a factor of 2 in terms of the magnitude of that difference. Okay, and so at this point, I would be pretty happy about sort of going through and addressing. Now, I could go through and look at whether or not people in the express condition, for those individuals in the express condition, if those people who are watch the sadness film show more emotion than those in the amusement, and for the people in the fold, if they show more expression than those in the sadness film. But that's not really part of why I'm doing this study in the first place, right? So yes, I could do it, but I don't need to do it to address the question at hand, and so I'm going to go ahead and set that aside on the table. People kind of see how this is, how we've gone through, constructed this? Okay, cool. So let's set this aside. Let's jump into one more example of going through and maybe running some contrasts. Okay? So go through and open up the data set, the trauma beliefs data set, the 2x3 trauma beliefs. Okay, so we're not going to go through and screen this, but if you go through and sort by gender, looks like we've got a case there that's missing. And get rid of that. And it looks like I got a class missing a bunch of people here. So get rid of those. And that should leave me with a full set. Okay, cool. People with me on getting sort of missing variables cleared out of that set? Give me a thumbs up if you got it. 2, 3, 4. Good. Okay. All right. So if you grab your 2x3 ANOVA handout here, the trauma beliefs one, this is what we're going to be working with here. What we've got is we've got participants, men and women, who we've given a PANIS to, right? This is going to be our outcome: positive affect, negative affect, and we've broke people into 3 different classes based on their perceptions of negative beliefs about trauma and its consequences. So we've gone through with some different analyses, separated these people into 3 different groups. We've got people with some interpersonal concerns about trauma survivors. These are people who say, oh, I'm worried about having a relationship with someone who's been exposed to serious trauma. I would be hesitant to have be in a romantic relationship with someone exposed to serious trauma. Some interpersonal concerns. Then we've got a benevolent group that these are people who are saying, yep, people with who've been exposed to serious trauma are resilient, they're good, you know, they're just as reliable and supportive as anybody else. And then we've got a group of people who are saying some negative stuff. You know, people who are exposed to serious trauma are unpredictable, they're dangerous, they never know what's going to happen, they're likely to fly off the handle at any point in time, right? And so what we want to do is we want to go through and sort of start to look at whether or not we're seeing differences in overall just regular, because maybe people who are saying negative things are just kind of just generally cantankerous. And maybe people who are saying nice things are just generally kind of positive, right? And so what we want to do is we want to go through and see if we have differences across our, differences in positive and negative affect across our belief profiles. But we also want to see if if any differences we see across belief profiles is dependent on participant sex, right? So we want to see if men and women within these profiles are responding differently in terms of overall positive emotion, positive affect, and negative affect. Okay, so we've got a 2x3 design here. First factor is participant sex. We have male and men and women, and then our second factor, 3 levels. We're looking at our 3 belief profiles based on a different questionnaire. Okay, and so here I've got 4 different hypotheses. Okay, so for positive affect, I'm saying that women will show more positive affect than men. Okay. Hypothesis 2 for positive affect, I'm expecting my benevolent profile to be greater than my negative profile combined with my interpersonal profile. Hypothesis 3, for negative affect, I'm expecting men greater than women. And my fourth, for negative affect, I'm expecting my negative group to report higher levels of negative affect than the combination of my benevolent group and my interpersonal group. Okay. So here I've gone through and I've made some different predictions about what I think is going to happen here. Okay. And so based on the way these hypotheses are structured, what am I going to want to use to tease these things apart? Can I use pairwise tests with this? No, why not, Laura?
Because some of the hypotheses want to combine two profiles.
Yeah, I've got some joint stuff going on there, right? So I've got some combinations of things. So I'm going to need to use some linear contrasts with this, okay? And so within this design, I've got 3 questions that I can ask, right? Is participant gender related to mood? Do belief classes differ with respect to mood? And is the relation between class and mood dependent on gender? Okay. These are the 3 things. So these questions correspond to each one of my 2 main effects and then the interaction effect here. People with me on this? All right. So we'll pretend that this is all well and good in terms of screening stuff. And so what I'm going to do is I'm just going to jump in and start running my model. So I'm going to start with analyses of positive affect. So I'm going to analyze general linear model univariate. Say positive affect is going to be my dependent variable. And then gender and class both going to be my fixed effects. Then I'm going to go down to options. I'm going to request marginal means, just it gives me a nice eyeball of what things are going on. I'm going to ask for descriptives, estimates of effect size, and homogeneity of variance test. And hit continue. You guys go ahead and hit paste. I'm going to go ahead and hit OK. Actually, here, I'm going to close this out so I don't get confused with stuff. All right. So if I'm going through and taking a look at my output here, I got men, or women, men, each one of my profiles. Do I have a balanced design here? No, don't have a balanced design. So I need to take that into account because that's going to impact sort of how I would move through and start teasing things apart. Okay. Looking at some descriptive statistics again. Here's main effect of gender, main effect of my belief profile, and then each one of these cell means these are going to be where my interaction effects are found. Okay. Looking at my quality of variance test. Layla, do I have concerns about violation of homogeneity of variance? Nope, things are looking good, right? So I've got an unbalanced design, but in terms of positive affect, it looks like each one of my cells are, across my 6 cells, I don't have too much of a concern in terms of violations of homogeneity of variance, okay? What if I go down and take a look at my effect table? Kate, what am I seeing here? Yeah, it's a fat load of nothing, right? I don't have main effect of gender, right? So I don't have evidence of systematic differences in positive affect across men and women collapsing across condition. I happen to also don't have a main effect of class. So collapsing across gender, it looks like my negative profile, my benevolent profile, my interpersonal profile aren't differing in terms of positive affect. And it looks like there's no interaction effect going on here. So in terms of my hypotheses, what do I do from here? So this is a wash. There's nothing to move forward with, right? So I guess that was no good, and that was no good. So this is actually, because these are decent cell sizes, right? It's kind of amazing that nothing just kind of popped up. But it looks like in terms of positive affect, there's literally nothing really to talk about here based on our analyses. So if I go through, do the same thing, I go analyze, general linear model univariate. I'm going to replace positive affect with negative affect, okay? And then I'm going to go down to the options here. And I'm going to go through, I'm going to hit this compare main effects box. Just to kind of show you what this is doing. Basically, this is going to run tests of my main effects. And then you can have LSD, which is no correction for anything, bond for any done SIDAC. I'm just going to choose LSD, and I'm just hit continue here. I'm going to go ahead and hit paste. Or well, I shouldn't hit paste, I should have hit this. Go ahead and run this. All right. So now, once again, same thing here. This shouldn't change, right? Because I should have sort of everybody in the set should have this, same people in each set. Here's main effect of gender, main effects of belief class, and then individual cell means are going to be my interaction effects. But Haley, do I have concerns about homogeneity of variance here?
Yeah.
Yeah, I do, right? So now all of a sudden I've got a situation where I've got violations of homogeneity of variance, I've got unequal cell sizes, and so all of this starts to make me very, very hesitant about just going through and pulling error terms from my ANOVA table and pretending like I haven't violated any of my assumptions. So I'm probably going to want to follow up with a different structure of things. Right? But if we go down through and we take a look at my tested between subjects effects. Amelia, what am I seeing here?
We do have quite a few positive or significant results.
Okay.
Our omnibus is significant. The main effect of gender and class are both significant, and the interaction effect is significant.
Okay, yeah. So not even anything that we might kind of pretend. It just looks
Yeah.
like there's nothing going on there with the interaction. But I've got a main effect of gender, and I've got a main effect of class, right? So Nick, tell me, my main effect of gender, can I interpret that right now?
Yeah.
Yeah. Yeah, what do I, tell me how I interpret my main effect of gender.
You just look at your total means for male and female.
Yeah, right? And so, I mean, our observed means are up, our marginal means are right here, just sort of eyeballing your marginal means. How do I interpret this main effect of gender?
Negative effect for females is higher than that of males.
Yeah, so collapsing across belief profile, what I'm finding is that women are reporting higher levels of negative affect than men, okay? Now, I predicted the opposite, right? So that's gonna be important to recognize and to note, right? But what I would do here then is maybe go through and just based on my, do I need to do any more statistical tests with this in terms of follow-up? No, right? I can just report my F statistic. I've only got 2 levels. I can say this group is bigger than that group. I can go through calculate I can calculate an effect size based on my observed means, right? So here's my mean for women. Here's my mean for men. There's my this is my standard deviation. I've got everything I need to just go through and just calculate hedges G and just talk about that. Case closed with that, right? Feeling all right with that. Sound good? Cool. All right. But I've also got this this main effect of class. And Evelina, can you tell me what that main effect of class suggests?
That people in the middle class display more negative affect and those in the
Maybe. Can I tell that based on the omnibus effect? Yeah, so I've got 3 of these. I need something so I've got a main effective class. And if I look at that main effective class, it's saying collapsing across gender, at least one of these classes differs in level of negative affect than the others. but I don't know which one, okay? But luckily for me, I've gone through and I have very specific hypotheses about what may be going on with this, right? Now before we go through and investigate that, so you go down through here and you'll notice that we have estimates. So here you have your marginal means, and then you have pairwise comparisons of your two genders. So this is the difference between men and women, women and men, right? So it's just the same thing. When we requested main effects, tests of a main effects, that's what this is giving us here. Now, the issue is what's going on is these tests are calculated using Fisher's LSD. Like if you go back to your last slides and look at how that's actually calculated, this is all pulling estimates from your overall factorial ANOVA table in terms of your error terms and things like that. Did we decide that was a good thing to do? Probably not for this one, right? We've got violations of homogeneity variance, we've got different things going on, different cell sizes. So we probably don't want to look at this, but it's something that you can request from SPSS. Same thing, we've got your marginal means for class here, right? And then these are just pairwise comparisons across your class differences, right? Again, using formula for Fisher's LSD. Now again, I'm nervous and I don't know if I put a whole lot of stock in this because I've got a lot of violations and I'm not comfortable just pulling terms from my ANOVA table. Also, am I interested in all possible pairwise comparisons here? No, right? I have specific hypotheses that I want to go through and test. So I'm probably not going to pay too much attention to this. And then here down at the end, we have marginal means by cell for gender and class, but we didn't get an interaction there, so we're not going to worry about that. Okay. But I want to go through, and I have some specific contrasts that I want to calculate based on my analyses, right? But I know that if I'm going to go through and I'm going to calculate my contrasts, I want to have, for that formula, I need to have an estimate of my mean squared error. But I'm not comfortable just using mean squared error for my overall ANOVA table, right? Because of violations, homogeneity, variance, and stuff like that. So what I'm going to do to probe this, this main effect of, to run my actual tests here, I'm going to go through and I'm going to go analyze. I'm going to go to compare means. And I'm going to go one-way ANOVA. Okay. I'm going to look at negative affect by class. And then I'm going to go options, get Welch, descriptives, homogeneity, variance stuff. And hit OK, continue, and I'm going to hit OK. All right. So what I'm doing with this, I want to go through and calculate some specific contrasts because I think I'm predicting that my negative group is going to have higher levels of negative affect than the combination of my benevolent and interpersonal group collapsing across gender. Now, and again, I'm concerned about just pulling my error term for these contrasts from my factorial ANOVA because I've got some violations. So what I'm going to do is I'm going to say, okay, well, for the purposes of teasing this out, what I'm going to do is I'm just going to go and rerun this using just a one-way ANOVA design because that's going to give me I'm more confident about stuff that's going to be going on there. So if we look up here, this should look familiar. We've got means, cell sizes, means, standard deviations. Just looking at differences across your conditions. And we do see that we've got a violation of homogeneity of variance here, right? The distribution or the variability of negative affect across these different cells, across these different classes. I mean, we've got a big sample size, right? So this is a sensitive test, and if we go through and we take a look at the actual differences in our variances, it's probably not huge. It's about a 2-to-1 difference. whether or not that's a big deal, probably a lot of what's driving that Levine's test is the fact that we've got a whole lot of people in this sample. But still wanted to take into account that we do have some evidence of differences in variance across cells. We've got some pretty large discrepancies in terms of cell size, and so we want to respect some of this stuff, okay? So we go through, we see for our ANOVA model, we see significant effects. If we go down to our robust, so our Welch's test, our Welch test actually says we don't have effects there. But are we running this ANOVA to test for significance tests? Are we running this whole thing to determine whether or not there are differences across my different class groups? No, I already did that, right? I ran that, I got that in fact out of my Factorial ANOVA. All I'm using this as a way to go through and get the things that I need to get in order to run my contrast, my planned contrast that I had on the front end, okay? So what I'm gonna do is I'm gonna say, all right, what are my contrast weights here gonna be? So my interpersonal concerns, what's my, what's the weight of my contrast gonna be there?
-1/2.
-1/2, perfect. And what about for benevolent?
-1.
Excellent. And what about for negative?
1.
Perfect, okay. Pitchfork statistic, all right? I'm gonna go through and I'm gonna take 0.5 times 14.844 minus 0.5 times 15.024 plus 1 times, or 1 times 16.898. And give us a value of our contrast of 1.964. Okay? Comfortable with that? Standard error. Standard error is going to be the square root of my mean squared error from my, and so we talk about this as a simple effects ANOVA. And so what's my mean squared error going to be for my standard error here? You got it, Evelina?
Is it the within groups?
What's that?
Is it the within groups error?
Yep.
So 11,107.
Oh, that's between groups. Mean squared error, right? 35.145, all right? And then we're going to take this times, remember for this formula, we're taking the square of our weights over our sample sizes. So I've got 0.5 squared over 138 plus 0.5 squared over 120 plus 1 squared over 75. Now if I run all this, I'm going to get a standard error of 0.778. Hey, what do I do to calculate my test statistic then?
We find a critical value.
Okay, yeah, we can find the critical. We'll worry about critical value. What about the test statistic?
Oh, we take our linear contrast value divided by standard error.
Perfect, yeah. Just linear contrast, 1.964 over my standard error, 0.778. Gives me a test statistic of 2.52. And so now in terms of critical value, my T-crit, how many degrees of freedom am I going to set this critical value against? Evelina, I'm sorry to keep picking on you, but you're looking in the right direction. What's the degrees of freedom I would use with this? Yeah, exactly. 330. We're going to use the degrees of freedom associated with the error term that we're using, right? So T critical with 330 degrees of freedom is gonna be 1.967, right? We see that our test statistic exceeds that, right? This is actually, if we go through putting a p-value calculator, this is gonna be associated with p equals point, I don't know, it's whatever. I thought I had that written down. It's like 0.002 or something like that, right? But we can figure that out later. And so, do we claim evidence for our hypothesized contrast here? Yeah, right? It looks like, yes, based on the data we've collected, it does look like that indeed individuals in this negative profile are reporting higher levels of just generalized negative affect than individuals in the combination of our interpersonal and our benevolent profile. Okay. Last thing we might want to do is calculate an effect size for this, right? Now, what I can do, and what seems like maybe an attractive way to do this, is just take a pooled variance estimate for the combination of these three groups, right? So if I go through and I calculate my pooled variance as 137, right? This is 1 minus people in the first group times 26.905. It's going to be my variance of group 1 plus 119 times 33.328 plus 74 times 53.319 all over, well, essentially 333 minus 3. Right, so we're just taking that pooled variance formula and we're just expanding it out to include however many pooled groups that we will have in there. Okay. Going to give us a pooled variance of 35.144. So I want to calculate G. Take the value of my contrast, 1.964 over the square root 35.144. It's going to give me 0.331. So again, I'm interpreting this as, yes, so positive affect stuff was a wash. That didn't turn out, right? But for negative affect, I found a significant effect of gender, which is in the opposite direction that I had expected, but it's something worth noting. And then in terms of my belief profiles, I had very specific hypotheses. I expected that my negative group was going to rate higher levels of negative affect than the combination of my interpersonal and my benevolent. If we go through and we run that, we see that that's actually, we have evidence for that effect. We do see higher levels of negative affect in the negative group as opposed to the other two. And we see very specifically that my negative group is reporting about a third of a standard deviation higher levels of negative affect in the combination of my interpersonal and my benevolent groups. Okay. People kind of went through that pretty quickly, but people kind of follow this? Okay. Question. Do we need to do all this by hand? Angelina's shaking her head. No, in fact, we didn't, right? But I did want to go through and show you how you go through and do that. If we were to go through and do it by hand, for these types of things, easier thing to do if we go back to analyze, go to general linear model, or excuse me, compare means, go to our one-way ANOVA. We go to contrasts. So our first contrast, or our first weight is what?
-0.5.
-0.5. Add -0.5. Add, and our final weight, 1. Add, continue. Just go ahead and run that. SPSS will just do this for us. Now, what's the benefit, in theory, of running this in SPSS?
They use more exact terms.
They use more exact terms. Yeah, what else? precision. Well, in theory, we've got to have any correction for violation of homogeneity variance and unequal samples. No, right? So we just kind of ignored it, right? SPSS has a procedure that they're reporting as a correction for violations of homogeneity variance. Now, the extent to which this is an acceptable correction, I don't know. Again, I've been not optimistic based on some sort of digging that I've done. But if we go down through and we take a look at our contrast sheet that we just ran through, we see value contrast, that's looking pretty close to what we got. Standard error, that's looking pretty close to what we got. Test statistic, is that looking close? Yeah, looking pretty close, right? This is nice. When we run things using the same formula as SPSS and get roughly the same numbers, I like that. That makes me happy, right? But we also have this other formula. And again, you have the formula. You could do this by hand. It would require some calculations, right? But SPSS is going to do it very quickly. And again, we're seeing functionally the same. I mean, we're still some downward correction for violations here, but we're still getting the same type of thing. So again, probably an easier way to go about this than cranking things out by hand. But depending on the situation, I want you to know kind of how this stuff is gone through and done. Yeah.
What do you expect in our problem set?
Huh?
Are we expected to do this by hand or?
If I don't tell you to do it by hand, use SPSS, okay? In general, unless I say do it by hand, use this. It's easier on you, it's easier on us, and it's more likely how you're gonna go through and approach this stuff down the road, okay? All right, so this was a little bit different. We didn't have an interaction here, but what we did have is we had a main effect that we needed to go through and follow up, but we had some concerns about differences in sample size, violations of homogeneity of variance, and so we took a little bit different approach with this, okay? People comfortable with this, kind of get this sense for what we're doing? All right, cool. Let's finish up with these last couple of slides on post hoc stuff. All right. Now the issue is, with our factorial designs, particularly with our interactions, how many pairwise comparisons can we make with our 2x2, did we say? How many reasonable comparisons could we make? 4, right? We've got 1, 2, 3, 4. So 4 comparisons here. Or 2x3? 9, okay? We got 1, 2, 3, 4, 5, 6, 7, 8, 9 comparisons that we can make. What about a 3x3? 18, right? We got 1, 2, 3, 1, 2, 3, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? Now we've got 3, 6, 9. 9 times 8 is 72. 72 divided by 2 is 36. Yeah. So there's 36 possible pairwise comparisons in here. Only 18 of these are viable, right? In a 3x4 design, we've got 30 reasonable comparisons. A 2x2x2, we've got 12, right? A 2x2x3, 24, right? So even though with our interaction effects, the number of reasonable comparisons that we can make is going to be a significantly smaller number than the number of all possible pairwise comparisons that we can make. As our designs start to get increasingly large, the possibilities of going through and probing these interactions get really huge, right? And so what ends up happening is if we just go through in SPSS and we just ask SPSS to give us post hoc tests, how many tests is SPSS going to correct for? Is SPSS going to be careful and only give you correction for the number of possible tests that you could, or interpretable tests in these interactions? No. It's going to correct for all possible comparisons, right? So, if we're talking about a 3x3 design, there's 18 real comparisons that could be made. How many is SPSS correcting for? 36, right? This starts to be a huge, huge issue because what SPSS is doing, it's going to control for all possible pairwise comparisons, and that's going to be a huge overcorrection for what you're actually doing. This is going to impact your power. The correction for your family-wise error is going to be way too much, and so you're going to have reduced power of your test. Those things that you should be able to claim as statistically significant aren't going to be significant because I've just corrected for 72 comparisons when I only wanted to correct for 18, right? Now, that's still 18 tests that you're on the hook for explaining, but you start to see why post hoc testing with factorial designs starts to become very difficult, right? Starts to be complicated. Some things that you can go through and do. This is something that I had people do, and this is based on some writings from Howell about going through, and we talked about this before in the ANOVA design, talk about hijacking Tukey for our own purposes and trying to modify things. So what we could do if we wanted to Tukey correct for a post hoc comparison of an interaction effect, right? I'm going to go through and I'm going to determine how many possible pairwise comparisons could be made, right? So let's get, I've got a 2 by 3, I've got nine comparisons that could be made, right? And so what I want to do is say, okay, I really do want to compare all possible pairwise comparisons within the context of this interaction. This is exploratory, they're all potentially kind of interesting, I just want to go through and look at everything, okay? So I've got 9 comparisons that I want to make, okay? What I can then do is go through and find a value of R that gives us some reasonable level of protection against type 1 error, okay? So again, 2 by 3 interaction, I've got 9 meaningful comparisons. Now remember, Tukey's based on that R, or the number of means, in one way ANOVA, if I say I've got 3 means, then Tukey's just going to correct for how many comparisons? 3, right? If I've got 4, it's going to correct for 4 times 3 is 12 times 2 is 6, right? And so what I want to do is I want to go through and say, all right, I need to correct for 9. So what Tukey R can I specify that gets kind of close to 9? Well, if I say 4, if I set R equal to 4, that's going to correct for 6 comparisons. 4 times 3 divided by 2 is 6, right? If I hit 5, 5 is going to correct for 10. 5 times 4 divided by 2 is 10. Now, so I've got 4 is too little if I want to correct for 9. 10 is a little conservative, but maybe I go for 10, right? Or maybe I go for 4, but I sort of set my alpha to 0.01 or something like that, right? Some different ways you can go through and do this. But let's say I go through and I want to say, okay, I'm going to correct for 5. I'm going to set 5, I'm going to be conservative here. So I set R for 5, and then what I'm going to do is I'm going to calculate my critical Q based on my chosen R and my degrees of freedom for my contrast. So what I do is I go through my Tukey table or get an online calculator, find what my Tukey Q is going to be if R equals 5 and the corresponding degrees of freedom. And then what I can do is I can translate that critical Q into a critical T. And then what I can do is I can go back through this and I can compare this and 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 that and here and here and here and here and here and here. I just run through all 9 of those, and what I'm going to do, just with an independent sample t-test, and then I just compare that t-test, whatever t-statistic I get, to my new critical value that I've got with a Tukey correction with R equals to 0.5, right? And then what I can do is then say anything that exceeds my critical T that I've derived from Tukey, any of my independent sample t-tests that exceed that, I'm going to say, I'm going to count these as statistically significant with a modified Tukey correction, okay? So this is something that you can use, but it's not precise. Howell talks about this as an option in some online materials, but it gets a little squirrely in terms of like, it's not precise. So there's no precise estimate. It's just like I'm providing some level of correction for some stuff, okay? So another option we have, something called Benjamini-Hochberg approach, okay? Benjamini-Hochberg is more interested in false discovery rate than family-wise error, right? So with family-wise error, what we're doing is with family-wise error, we're concerned about the possibility of committing 1 or more type 1 errors, right? Saying that we have an effect when there's not, right? But with this approach, we assume that even if we make one type 1 error in the whole set of comparisons, that we've failed, right? I'm running 6 comparisons, right? 5 of my comparisons are right on. I haven't made an error. One of them is the whole thing's gone to garbage, okay? Benjamini Hochberg is asking what percentage of my significant effects are false positives, right? So I've gone through and I've found a number of significant effects. How many of these are likely to be false positives? So it's taking a slightly different approach. And so what Benjamini Hochberg does is I've gone through, and let's say I've got 9 comparisons. So I go run through and I run 9 different t-tests, and I go through and I take a look and I line those t-tests up, starting from my highest p-value, right, my least significant p-value, down to my smallest p-value, or my most significant test. And what I'm going to do is I'm going to go through and I'm going to use this formula to go through and calculate a specific p-value for each one of those tests. And as the number of tests increases, my tests get stronger and stronger, that p-value starts to get lower and lower in order to claim statistical significance. So my p-critical for any individual test is going to be I, which is the test index, starting with 10 as the least different test, all the way down to 1, which is the most, over k, which is the number of tests, times my alpha level. And so if I do this for my 2x3 ANOVA model, okay, so I've gone through and I've run these contrasts. I've ordered them so that my smallest test statistic, or my weakest, or my smallest p-value is listed first, all the way down until I get to my my largest difference, or my most significant test, right? And so then I line up these up in terms, here's the p-value I observed in my test, here's my index. My lowest is 9, 8, 7, 6, down all the way down. And so then I have for each test a new p-value. So for my lowest one, my least significant test, if we want to talk about it that way, my index is 9, divided by the number of tests is 9, times my alpha level, 0.05, so my p-critical is 0.05 for that, right? And then we go down to the next one. This is index 8, 8 divided by 9 times 0.05, I got 0.044. And then work down through this, right? And so we see here, by the time we get to this test, we have normally, at just a per comparison error rate, something that we would identify as statistically significant. But my Benjamini Hochberg critical P is 0.039, and so we wouldn't say that Benjamini Hochberg would say that this is maybe a false positive in here, right? But by the time we get down to this one, we get a p-value of 0.018, my critical P 0.033, we would count this one. Down, 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 keep going on and on, right? So it's a different approach, and it's providing a more exact correction than my modified Tukey approach, okay? And so if I have a set of tests, and I'm wanting to go through and I'm going to look at all possible pairwise comparisons within the context of my interaction term, this is a nice approach that you can go through and say, all right, based on this, I really don't have any a priori hypotheses. I really am looking at all possible comparisons within the context of this interaction effect. This is a nice option for going through, because then you can say, all right, I've got, let's say you really do have 18 possible pairwise comparisons. Run all possible 18, stack them up, line them up using this Benjamini Hochberg, and then you can say, all right, using this procedure, this is a correction, these are the effects that we can say are statistically different within the context of this interaction. Okay. Questions about this? All right, I've got a screencast video for running through an additional screening, running through the modified Tukey, and running through the Benjamini Hochberg that I'm going to go through. You guys can go through and take a look. It'll be some extra time outside of class, but trust me, just walking through some of these videos is going to be very helpful in terms of getting your head around how to go about looking through some of this stuff. Okay. Last thing we'll talk about here is some higher order designs, right? So here we've got, say three factors. We got factor A, factor B, factor 3. what we're gonna end up with here is a main effective factor A, main effective factor B, main effective factor C, an interaction of A and B, an interaction of A and C, an interaction of B and C, and then a three-way interaction of A, B, and C. Now the three-way interaction stuff starts to get a little bit tricky, right? We're talking here about a higher order interaction, 3 or more factors, and what we start to work with here in thinking about taking the same principles that we've talked about in terms of conditional effects and transporting that into the higher order effects, right? So in this case, if I've got a 3-way interaction, right, that's statistically significant, can I make an interpretation of my 2-way interactions? No, because they're conditional, right? My interactions are now conditional effects, right? The differences in the effective factor A across factor B are now dependent on factor C. The nature of what this interaction looks like between A and B is now modified by this other factor, right? And so when you think about this as behavior of the first order interaction and all subsequent simple effects dependent on some higher order variable, right? So if I got a 2 by 2 by 2 ANOVA, what I've got is an interaction of A and B here, an interaction of A and B here, but the nature of this interaction looks different whether or not we're talking at about level 1 of my third factor or level 2 of my third factor. Who's confused by this? Yeah, because they're confusing stuff. Main takeaway from this, right? We're not going to get in, I'm not going to make you to go through and probe higher order interactions or 3-way stuff. If you're running a 3-way interaction, come talk to me, I'll help you to work through and disentangle that stuff. But what you should take away from this, be very, very, very careful as you're designing your studies, okay? What happens is you like, oh, I want to look at this, and I want to look at this, and I want to look at this, and I want to look at this. Well, now all of a sudden I got a big ass design. I got to get a bunch of people in. And then there's a possibility I'm going to have some sort of 3-way or 4-way interaction. I've got a sort of 3 levels of this factor and 4 levels of this factor and then 2 levels of this factor. Now I've got a giant interaction. Probably not because they're hard to detect, but now I've got to go through and sort of explain this somehow, right? So as you're going through these types of designs, make sure that smaller is often better than bigger, right? You don't have to account for all possible things in a single study. Make sure that factors that you're using are things that are theoretically important, that things that you go through and you have an idea of how things should turn out, and then have an idea, some a priori hypotheses as you're putting this stuff together about, if I were to find an interaction, what would I expect that to look like? How would I expect these means to differ? Which are the things that I would want to go through and tease apart? You're going to be in a much, much better situation than now all of a sudden John's got a 4-way interaction on his hands with 72 possible pairwise comparisons, and good luck in trying to figure out how you're going to tackle that thing, right? So just because you can do something doesn't mean it's a good idea to do something. So be judicious as you're starting to put these designs together, because they start to jump out of hand quick. Okay? Awesome. All right. Any questions? Okay, you guys have been fantastic.